work and energy. You'll often see these two things written together. In fact, they're kind of the same thing. It's like looking at energy in two different ways, as we'll see. Work is sometimes defined as a change in energy, and energy is sometimes defined as the ability to do work. We're going to start with the idea that work is a change in energy. So to help you get a visual on this, because energy is a difficult thing to visualize, we'll just take a little aside here. And let's imagine a bank account. I like to think of energy as a bank account. I think I've used this analogy before. Bank account. Okay. So if energy is a bank account, if you have sort of zero money and you go to work, you can increase your bank account and you can get some money. And the way you do that, of course, is by going to work. So the change in your bank account is because you went to work. See? Now you have more money than you had before. If you go out on the weekend, on Halloween, and you spend all your money, your bank account can drop. And if you spend more than you had, you can even go into the negative numbers and have sort of less money or money taken away, owing money. And this is kind of like the opposite of going to work. Going to work makes money, going out and partying spends money. So it's like the negative of work, or the opposite of work. So when work is done, you make money, and when you spend it, you lose the money. That's like sort of, well, you could kind of make it, you could kind of say that the money works for you, right? You work for the money in the red part, but when you spend it, the money works for you. So you can see that your perspective is kind of important when you're trying to figure out how this work business works. So in physics, if we just think of energy as the money, then work causes an increase, right? If you do work on something, then it causes the energy of that object to increase. The energy of that something. Increases. Okay. And likewise, we can make another statement, the opposite statement of that. If something does work on something else, on another thing, we're going to have all these things here. If something does work on another thing, then the energy of the something, the original thing, decreases. Decreases. So when you do work on something, it's almost like your energy level is decreasing because you're giving that energy away to something else and increasing its energy. So it's this constant trade-off. All right. And we have learned in previous years that work can be described of as a force multiplied by a displacement. I'm going to say displacement. We sometimes say force times distance, but I'm going to try to use displacement because the directions are a little bit important here. What's important is that this force is the applied force, not the net force. A lot of people confuse that. It's the applied force, not the net force. And it also must be in line with the displacement. That's why we're going to use a little mathematical trick to ensure that that happens. Let me show you what I mean. If you take an example and you want to push a block or pull a block, let's say you push the block this way with your force applied, and you move the block through a distance of displacement of so many meters, right? You can see from the picture that the force is in the same direction. I'll put an arrow on the displacement here. The two are in the same direction. They're lined up. They're in line with each other. The problem is that we don't often do things this way. When we push on objects, we often push on an angle. So let me put an applied force, I'll put it here, pushing down. Say you're pushing on the back of this box and you want to move it. And if you move it across the floor, a distance or displacement here, you'll notice that now the applied force is not in line with the displacement. So you cannot just calculate this red force times this green displacement as it is. What you need to do is find out how much of that force is in line with the displacement. So to do that, you would need to know how much of this force is straight down and how much of it is going over here, so the two green arrows there are lined up. See? And if I told you what the angle was, if it was an angle of theta, then you know how to do this already. We've done this resolving of vectors many times. This green side here would be F applied times, since it's adjacent to the angle, cos theta. And the one over here would be F applied sine theta. But this one has no effect on the work done, because you notice how it's completely perpendicular to the displacement. So we don't really even care about this one right now. Any force that's pushing down is pushing into the floor, and the normal force of the floor is pushing back, and it's kind of a wash. So it's the component in the direction of the displacement. So when we write the expression now, it's F applied cos theta multiplied by D. See that? And we often write this in a slightly similar way. We don't like all the brackets. So if you were to write without the brackets, you would get this, F applied theta times D. And now it's difficult to tell what's going on here. Oh, I forgot the cos. Hang on a second. Let me erase that. F applied cos theta. That's kind of important. And then the D. See, what's happening here is it cos of theta times D, or is it the cosine of theta times D? Is the argument of the cosine function both of these, or is it just one of these? So that's confusing, isn't it? So what we do is we just realize that what this expression is it's an applied force multiplied by the cosine of an angle multiplied by D. And since the order of multiplication doesn't matter, we can multiply them in any order. We tend to write it like this. We put F applied, then we put the D, and we just stick the cos theta on the end so that the argument is not messed up. So this is how we tend to use the the work equation. And a little cos theta is there because what it does is it gives us the component of the force that is lined up with the displacement. That's what its purpose is. And we've already done this with components, so it shouldn't be too big of a deal. All right? So, a couple of examples maybe, just to do it really quickly. Let's actually work out one question. Let's take this, let's make it 10 kilograms. Let's let me move this up a bit, and we'll apply a force. Well, you know what? We can pull it this way. I just didn't want to get it. We'll pull our force this way. Push or pull doesn't matter. There's my applied force, and I will tell you that my applied force is at an angle of 30 degrees, and the applied force is 50 newtons. Okay? First, we're going to do a situation with no friction, just to kind of compare what happens. No friction. All right. So because there's no friction, I really don't have to worry too much about the normal force and the gravity force in the free body diagram. They're there, but the purpose of that is to tell me the normal force, which I use for friction. There's no friction, so it doesn't really matter, right? However, I do need to know what we have here and we have here, the components of my force. Okay? I'm also going to tell you that this box is going to move a displacement of, let's go 12 meters. So how would I calculate the work? Well, the work done is very simple. Work equals F d cos theta. And remember, the F and the cos theta are really telling me the value of this purple line right here, right? So I don't even need to draw the picture. I don't even need to worry about resolving it on here. I can just do it right in the formula. It's 50 newtons of force multiplied by 12 meters of displacement, and then it is cos of 30 degrees. And if we put all that together and multiply it, 50 times 12 times 30 cosine equals about 500, and if we round it off, 519.6, we'll just say 520 joules. Unit for work is joules because work is an expression of the change of energy, so it's still joules. All right. Now, interestingly enough, if we do the same picture, the same situation, but we include friction this time, let's look at how it changes. So let's start again. Here's the box. What was its mass? 10 kilograms? Good, 10 kilograms. We're going to pull it the same way, 50 newtons of F applied. And we're still going to use an angle of 30 degrees. The only difference is we're going to add in a mu here. The mu is going to be 0.2. Let's just say something small. Well, because we're adding in friction, now we also have to consider our normal force and our gravity force, Fg. And we have to now consider, remember when we were doing work, I said that the F applied sine theta didn't matter for work? Doesn't matter for work, but it does matter for the normal force. Because if I pull this way, that's the one I want for the work, but pulling up is an upward force. It's part of my F net y now. It's going to change the normal and the friction. So if I start with an F net y, like we've done before, we'll see there are 3 up and down arrows, aren't there? There's Fn, there's Fg, but there's also what I'm going to call F applied y, which is this purple guy right here. But we know what he is. Fatty. He's F applied 50 times the sine of 30, which is a half. So he's actually worth 25 newtons upwards, right? Now, if we push a block, we always make the assumption, unless we're told otherwise, that when you're talking about doing work and pushing things, nobody pushes things in such a way as to accelerate them. It's kind of silly. You just push at a constant speed. So unless the question specifically directs you to think about acceleration, or tells you things that hint towards acceleration, you can probably make the assumption that you're pushing the block at a constant speed. And just while I'm at it, I'll add in our displacement of 12 meters that we were going to push it, right? So constant speed means that the net force is 0. Now, of course, with F net y, we're not pushing up or down at all. We are kind of pushing up a little bit. There's 25 newtons up, but there's 98 newtons down when we do the weight of the object. So the object's not going to lift off the ground, so we're okay. So we go through this process to get our normal mg, mass, 10 times 9.8, and a downward force, an upward force, so that's positive, of 25 newtons, a lifting force. And so what we get here is Fn minus 98 plus 25, and when you move it to the other side, what do we get there? 73 newtons? is the Fn. 73, and of course we might want to put our newtons in there, but let me write 73 newtons. Notice how, in this case, the normal force is not equal to the weight anymore because of the additional upward 25 newtons. The floor is getting help from the person who's actually pulling. So the floor doesn't have to push as hard to support the weight. But that's my normal. Then we move on and we'll do our F net x as we normally would. F net x equals, now I've got F applied x, which is down here, 50 times the cosine of 30. And what is 50 times cosine of 30? 0.87 to 40, 43.3. Squeeze it in there. Just because we know we're going to need it. What else do I have sideways? Well, I guess now that I'm talking about friction, I would have to add a frictional force going backwards that works against me. And if I put that in here, there'll be a frictional force as well. Are there any other sideways forces? I think not. Now, again, we talked about pushing this at a constant speed, so there'll be no acceleration, so F net equals m times 0, ma, we're good with that. F applied x is 43.3, and the frictional force will be in the opposite direction. I believe I said 0.2 for the coefficient of friction. Is that right? Yeah. And multiplying that by the normal of 73 newtons. So if I just kind of continue that, we've got 0 equals 43. Wait a minute. Freeze. We have to have something to solve for. We don't really know if it's constant speed, do we? So we better put ma here, and it'll be 10a. And actually what we will have is an acceleration. It was my mistake to tell you it was constant speed. Normally we would push at constant speed, but because I picked 50 newtons, how do I know if that's too much? How do I know if that 50 newtons is actually going to push at constant speed or not? So it's 10a, 43.3, and what do we got here? 14.6 minus. So if we do the subtraction and we divide by 10, what do we get? .7. Okay, good. Meters per second. All right, so we did all that. Now, if we go back up here to the first question that we did to compare, we figured out the work quite easily. What would happen if we took a moment here, let me just erase this, and figured out the acceleration in this case to compare it? Well, obviously it would be a little faster, we would hope, because there's no friction. And because there's no friction, it's very easy to do. F net x is just equal to F applied x. That's the only force involved. So ma equals F applied x, which is 50 times cos 30, which was how much? No, 25 was the sine. 43.3. So when you divide that by 10 for the mass, you're getting about 4.3 meters per second, right? Squared. That's a much faster acceleration than the one we got here because there's no friction. It makes sense. Meters per second, and I noticed that should be squared. Now let's do the work in this case. Well, if we calculate the work equals F times V times cos theta. Now here's where you got to be careful. The number 43.3 that we have been using is F applied x. It's already F cos theta, isn't it? So we don't want to put 43 in there. We have two choices. We can either go 50 and cos 30, or we can use the 43 that we've already figured out, and that's just F cos 30 already done for us. So it's 43.3 times 12, and how much is that? $519, or pretty close to 520 joules. So let's look at that and compare to our previous situation. 520 joules 520 joules. So the friction has no effect on how much work is done. So what's the difference? Well, the difference is, in the first case, you would achieve that amount of work faster because you were accelerating for something. Here, you're accelerating slower. So what's actually different is the friction affects the amount of time involved in getting the work done, but it doesn't change the amount of work. If you do 7 homework questions in an hour, then somebody else does 7 homework questions in a day, it's still the same 7 homework questions done, isn't it? It's the same amount of work. It's just that the time has been affected or changed. Okay, and so that's basically how we calculate work, and when we're talking about forces and distances. However, I will also mention that that's not the only way to view calculating work. You can also look at work as a change in energy, right? And so that change of energy could be a change of EK, kinetic energy. It could be a change of gravitational potential energy, right? Which means there could be, 1/2 mv squareds in there, or there could be mghs in there. Anytime something changes height, the change in its energy is equal to the work done. So you don't have to worry about force times distance. Instead, you're looking at 2 different energies and finding the difference between them, right? Of course, delta means EK2 minus EK1. So if you have a bicycle going 2 different speeds, let's say it's going, let me show you. Bicycle, now let's spell bicycle right, just for the English majors. Bicycle, 2 wheels, right? That's what bicycle means. Bicycle is moving at 4 meters per second. And I guess I should give you a mass. Let's say it's a 40 kilogram kid on a bike or something, 40 kilograms. How much work is done in changing the speed to 7 meters per second, right? So work is equal to the change in the energy, which is EK2 minus EK1. I know it's EK because we're talking about speeds. So that's going to be 1/2 mv2 squared minus 1/2 mv1 squared. And of course you can shortcut this and put the 1/2 and the m outside, and it's just the difference of the speeds. Whoops. v2 squared minus v1 squared. Then you can solve that by doing 1/2 of the mass, which I said was 40, and the 2 speeds, I believe it was 4 and 7. 4 and 7. So the second speed is 7 squared minus 4 squared. Then we get a change in energy of 20. And 49 take away 16 is 33, I believe, right? So 20 times 33 is 660 joules of work done. So that's another way of dealing with work. It could be a change in energy. And you can imagine another example where you did a change in height, where instead you would have mghs in here. It's the same idea. So when you're dealing with work, don't just look for force and distance and say to yourself, well, this question doesn't have a force or distance, I don't know what to do. Look also for changes in energy. And I'm going to stop this particular video here and leave it sort of separate from what comes next.